Finally, the world is looking forward to the FIFA World Cup in Brazil. My name is Andreas Klump, and today, matching the theme, we are going to talk about a virtual free kick training. I will show you how to set up this free kick situation in SOLIDWORKS Motion and what kind of physics we are taking into account. First, we need to have a geometry. Not necessarily to have this nice stadium, but we need to have geometry for, of course, the ball, the wall, the goal and the goalkeeper. I am opening the motion study already created here at the bottom. The first physical effect we will take into account is the drag force. We will build the drag force components with a ratio to the total velocity. The components are dependent on the drag coefficient of a sphere. In this case, it is a function of the Reynolds number, taking into account laminar and turbulent flow, as well as the cross-section, the air density and the velocity squared. We will use the function builder to define the components. In addition to the drag forces, we will consider the acceleration due to gravity and of course the regions of the model that come into contact during the analysis. For the movement of the goalkeeper, we have created a linear and a rotary motor. In the last step of the setup, we have to define the kick itself. We can do that with an initial velocity on the ball and with the direction of the shot that is defined by two angles in a 3D sketch. With this we can calculate the first free kick. For a better visualization, I can activate the flight path of the ball to have it drawn on the screen as a line. I'm going to suppress the study details to have a better view of the free kick and how the ball hits the crossbar. From the top, we see that the flight path of the ball is a straight line. But we have more, of course, even more results to talk about. For example, the velocity plot. We clearly see the decreasing velocity in time due to the defined drag force, as well as the immediate delay when hitting the crossbar. In order to score a goal, I am going to reduce the initial velocity and add some rotation to the ball so that it curls to our left. To make this happen, we have to take into account another physical effect, called the Magnus Effect. The formula for the Magnus Effect is very similar to the one of the drag force. What's important here is the profile coefficient for a sphere, which is defined by the radius multiplied by the angular velocity divided by the total translation velocity. To make it a bit easier, we assume that the rotational axis is in the normal direction to the pitch and will not change over time. Therefore, we are left with a force in the x direction, forcing the ball along the arc. After we have added the force function to the analysis, we can start the second calculation. Now, we can clearly see that the ball is flying in an arc, but it is saved by the goalkeeper. When looking closer from another angle, we see an outstanding save by the goalkeeper, using his left arm to hammer the ball away from the goal. Looks almost as if I had that planned. But today's training will shortly be over as soon as we manage to score a goal in the upper left corner. To achieve this, I will increase the initial velocity again to place the ball closer to the crossbar and increase the angular velocity to place the ball closer to the left post. With the last free kick, we see that the ball touches the left post and the crossbar to finally fall inside the goal, and Germany is the new FIFA World Champion. Okay, after I woke up from my nice dream, I have to thank my colleagues from the French and the English team who have created the model and the simulation setup. Thanks Julian, thanks Nick. Hopefully you have enjoyed watching this video and have seen how easy it is to gain more insight to your products with the right tools. I wish all of you a great FIFA World Cup 2014. Auf Wiedersehen.